Hey guys, I don't know why that's a little crooked today, and we've been crooked, it's okay. Good morning to everybody. Lab this week, unknowns. Any questions about lab? Quiz will be returned during lab. Key has been posted upstairs, third floor. Any questions about lab this week? Yes?
Do you want to calculations in the lab report, or no? Because it just comes in approximations.
No, calculations are not needed. They're just useful. Useful.
If we work with a partner, should we include their
No, not necessary. Question?
Is our pre-lab going to be downstairs, or are we going to meet in the lab?
Downstairs, thank you. Downstairs. Okay, guys, acid-base chemistry. We left off with, first off, any questions on acid-base chemistry up to now? Let's see how we did on these here. The next couple of acid-base reactions. We've got this compound here, and we've got this compound here. Okay? What's the most acidic proton? What's the most acidic proton in the circle? Most acidic proton here in this reaction. This H on this carbon? H on that carbon, where's the most acidic proton? H on this. Yeah, there's your acidic proton right there. It's the most acidic. This is the most acidic. Okay, then now where's the base? What's the most basic atom in the circle? These are nitro groups. You'll see nitro in organic 2. You should maybe look at the Lewis structure of the nitro group. If you do, you'll see the nitrogen does not have a lone pair. The nitrogen actually has a formal positive charge. Nitro groups are not basic. What's the base here? Yes, the sp3 nitrogen. Okay, let's draw the H out. Okay, so we're going to do our acid-base mechanism. And you need to show bonds when you're doing mechanisms. So you need to show the bond out if it's shown condensed, which it probably is. Okay. Mechanism. These electrons, the basic atom is going to bond to the H. These electrons do what? They move on to the oxygen and become the third lone pair. What's the result of that? This guy, which has 3 ethyls, nomenclature, right? Ethyl groups, 2 carbon ethyl. That's called triethylamine. It's a common base. A little weak, but it's still a decent base. This nitrogen is now bonded to what? Hydrogen. Because we showed it right here. The electrons are bonding to the hydrogen. It's a very simplistic thing to say it's making a bond. That's how we show it. That's the mechanism. This is no longer a typical nitrogen. Look for charge. What's the charge? Positive, okay. What's the other species going to look like? Well, what's the other thing? We've got the benzene ring with the nitro groups. We can just show those condensed NO2, NO2. I've rotated this a little bit. The oxygen is between 2 of the groups. It's just rotated. How many lone pairs on the oxygen? 3, right? It had 2. Where did the third one come from? This arrow right here. The bonded electrons moved onto the oxygen as a third lone pair. What's the charge of the oxygen? Negative. Yes. There you go. There's your outcome. Using your mechanism arrows to get you there. We don't have to memorize this. You're going to have a hard time memorizing a million different acid-base reactions. One way to do it. Here's your outcome. Okay, which side's favored? Left or right?
Right.
We need to know the pKa of each acid. Acid on each side. What was the acid over here? This molecule? pKa of about 1. How acidic is that? 1. We're going to call that acidic or neutral or what? What if it was pH of 8? What would you call it? Okay, it's fairly acidic. That's fairly acidic for, what do you call that functional group here?
Alcohol.
A phenol. Phenols usually have pKa of 10. The presence of these nitro groups make it much more acidic. Okay? It's actually called picric acid. It's actually, the name of it's actually an acid. It's so acidic. Okay? It's also explosive. You gotta be careful with picrate salts. This would be called a picrate salt, but that's called picrate. Okay, this one. What's the acid over here? Which thing contains the H? This thing. What's its pKa?
10.
It's 10, right? Because what does this refer to? If that's a base, what does the pKa refer to?
Conjugate acid.
Conjugate acid. What's the conjugate acid? That thing. So it's what is really 10. Which is favored, 1 or 10?
10.
Weaker acid's favored, right? 10's favored. This side's favored. By how much? 10 to the 9? Yeah? Difference in your pKa units, 10 to 9. What's that, a billion? So at equilibrium, you have a billion of these. Focus on the picric acid. A billion of them is in the anion form, and only 1 out of a billion remains in the neutral protonated form. That's pretty much complete, you agree? If we turn that into a percentage, it'd be 99.9999999% that way. Question, is triethylamine strong enough to deprotonate picric acid? Yeah, I just told you it was. It's going to go that way. Triethylamine deprotonated picric acid. Terminology, right? Explaining the outcome? Yes, it is. How'd we do on that one? Any questions about it? One below. Comment on this? Well, I commented on up there. This is phenol without the nitro groups. pKa of about 10. pKa of about 5. What's the most acidic H in the circle here on this side? Right there. Okay. You can just consider this one molecule. We're looking for the most acidic H in the flask. That one. What's the most acidic base in the flask?
Nitrogen.
Right here. Okay. Let's draw our bond down so we can do our mechanism. All right. These electrons, bam, bond to H. These electrons do what? Move on to oxygen and become the third lone pair. And now what do we have? This nitrogen is now bonded to what? Hydrogen. And the charge of that nitrogen? Positive. And what's the other species going to look like? Oxygen. The H is gone. It's done, right?
No. Minus.
This is not sufficient? What do you want to do?
Negative.
You want to add lone pairs? 3 of them?
And it's a negative charge.
Add a negative? Okay. Let's do that then. Yes, you must have that. It's oxygen with 1 bond is no good. Okay, which side's favored? We'll see, what's the acid over here? This thing has the H over here, pK of 10. It acts as an acid. What's the acid on this side? What has the H? The H is now here. What's its pKa? 5. This acts as a base. The pKa given for it, that's what we usually do in organic chemistry. For bases, we don't ever give pKb's. We give pKa's. But the pKa of something that's acting as a base refers to the conjugate acid. Which side's favored, 10 or 5? 10. This side's favored. By how much? 10 to the 5? What's that? 100,000? At equilibrium, you have 100,000 of these and only one of these. So this is called pyridine. Is pyridine strong enough to fully deprotonate phenol? To take it over there to fully form the anion? No. Because if you have 100,000, you're only going to do one of those molecules will only be done. That's like nothing. Pyridine is not a strong enough base to do this. If you're looking to make, a lot of times we're looking to make like an anion. If you're looking to make this anion, pyridine is not the right choice of base. You need a stronger base. Okay, one more below. That's an H. I reckon this is just one molecule. That's all I see over here. All right. What's the most acidic H over here? Right here. You all should know why and the thought process of how to determine that. You got H here, you got H here, you got H's on nitrogen. This is an amino acid with a generic R group. You're learning amino acids, maybe biology classes. If the R group is a methyl, the name of this compound is
Serine.
I don't have biology wrong. Alanine?
It is
Alanine, yes. Okay. It will undergo an acid-base reaction with itself, like with another molecule of itself. So it's the same thing. If you want, just act like this is not connected. Oh, that's the acid. What's the base here? sp3 nitrogen, lone pair. You've got an acidic proton and an acid, a basic atom in the same molecule. Who cares if they're connected? They can still react. Now this may be internal, okay? Or we could show another molecule. I'm going to cut it off. And we can show this, taking the H, these electrons moving here. But then this happens a million times. The nitrogen of another molecule takes this H, on and on. And ultimately, what does the oxygen become ultimately? Electrons move on to oxygen. And so the oxygen is now what? 3 lone pairs? Now minus. And the nitrogen, which had 2 H's originally, now has what? 3 and a positive. That's the outcome of the acid-base reaction. Now, I'm just showing one molecule. We could show 2. But if I show 2, it'd just be 2 of those. And usually you just show 1. Again, it could be internal, Could it be? Could this lone pair take that H? It's a long way away. Carbonyl's in the way. Can this bond right here rotate? Yeah, it's a sigma bond. What if we instead drew this like it's the same molecule, just rotated. If this bond rotates, my arm rotates, the OH comes over here. Now if you want to show it internally, boom, it's right here. And these electrons move there and become the third lone pair. You can show it internally, so-called intramolecular. One, two, three, four, five. 1, 2, 3, 4, 5. Nice 5-member ring. 5 and 6 are good, we'll learn. You got the structure. This is a molecule which is, what's the net charge of this molecule? It's net neutral. But it has 2 charges. What do you call a compound that's net neutral but it has 2 charges like this in balance? You heard this term? Starts with a Z.
Zwitter ion?
Who said that?
Zwitter ion?
Yes, Zwitter ion. Z-W-I-T-T-E-R-I-O-N. Zwitter. Zwitter is probably German. So Zwitter ion. Net neutral, so is it really an ion? Well, I'd call it 2 ions, but yeah, it's net neutral. Which side's favored? The all neutral form with no charge separation, with no charges, or the Zwitter ion form? Well, what's the acid over here? Right there. What's its pKa of the carboxylic acid? About 4 to 5. What's the pKa of the sp3 nitrogen? About 10, but this really refers to what? Okay, conjugate acid. Which is favored, 5 or 10? Weaker acid's favored. This side's favored. So when you looked at amino acids in biology, did they talk about it being in that form?
Yes, sir.
Because that's how they exist. And we see that by understanding pKa's and the fact that you've got an acid and a base internally, and they're going. Question. How soluble in water is this compound? Highly soluble? No, not soluble? Absolutely no solubility?
Would it depend on the arching?
Yes, it would somewhat depend on the R group. But this is sort of the main end. Yeah, I agree it could. But average R group, how soluble in water is this? Would your answer be absolutely not? Or it look like it should have good solubility? What would you say? Why soluble?
Because it has lower bonds
And thus
and hydrogen bonding, so.
hydrogen bonding potential. It could hydrogen bond with water? Could it? Yeah. That's polar. So you have polar interactions with water, but particularly those are going to be called hydrogen bonds because they're going to have that hydrogen bond interaction, which we call it strong. Is it ionic? Yes, it's ionic because we have to know that it exists in this form. It's ionic. What do you know about ions in water? Very soluble. The fact that it exists as a Zwitter ion really makes it have a lot of ionic character, and it's very soluble in water. Yeah? So an don't know if you talk about hydrophobic versus hydrophilic R groups. Is that what you're getting at? Something like phenylalanine with a big benzene ring is pretty hydrophobic. That probably has less water solubility than something like arginine or serine, which has an OH group. Those are going to be, relatively more, but as a general statement, let's just focus on the part that's consistent of the amino acid. By the way, is there anything that goes in front of amino acid? A symbol? Alpha amino acid? As you'll learn later on in Organic 2 with carbonyl chemistry, first carbon here is called the alpha carbon, and the nitrogen's on the alpha carbon. That's why they're called alpha amino acids. Where if the nitrogen was on some carbon way down here, it would be called maybe a beta amino acid or something, but those are unusual. We're not as common as alpha amino acids. Okay, how does pH come into play? Henderson-Hasselbalch. Henderson-Hasselbalch equation is pH equals pKa plus log of B over A. In biochemistry, you'll derive this equation. How do you get to this point? But there you go. There's your pH relation between pH and pKa. B over A. B is the basic species, called the conjugate base. If you wanted that apply. A is the acidic species. The acidic species contains the H, has the H. The basic species does not. Okay? Has nothing to do with charge. Has to do with, does it have the H or not? If it has the H, we call it the acid. You can read some of this in summary here. If pH is greater than pKa, the basic species will predominate. If pH is greater than pKa, so if the pH is maybe 9 and the pKa is 8, that would be an example of pH being greater than pKa, right? Well, for this math to work out, what does this have to equal? 9 equals 8 plus 1. So you have math, you add math. So this has to be 1. The only way this is going to be 1 is if B is greater than A, if you know what a log is. Okay? So that's where that summary statement comes from. Let's try another. Let's see. 10 and 8, this would have to be what? 2. Y'all getting it? But again, for this to be 2, B has to be greater than A. Okay, that's where the summary statement comes from. On the other hand, if this was 6 and that was 8, all right, this is a difficult one here. What would this have to be? Negative 2. And the only way you're going to get a negative number if A is the bigger component. So that's where the summary comes from. Let's try this out. Carboxylic acid. With the methyl here, the name is acetic acid. Okay, you put this on your salad. 5% solution. Don't put pure acetic acid on your salad. Mix it with 95% water first and add in some olive oil or something else. Would be good. At pH of 7, okay? How does it exist at pH of 7? Which is blood pH, roughly. Well, we got to know the 2 possible species, the B and the A. Now, this contains the H, so that's the A species, it's the acidic species. The basic species would look like what? What does this look like after it acts as an acid? A base comes along, takes the H, what is it going to look like? It's going to look like this, right? Lone pairs, sometimes they're omitted. Largely comes from when you're doing on electronically, it's very cumbersome to add in lone pairs. And so this is often done, and then when your hand dries, it's just easier. You got to know the lone pairs are there, right? But you guys all know that there'd be 3 lone pairs there. That's what I'm trouble with, that you'd be able to show that. How many lone pairs on this oxygen? 2. It's basic structure, which we talked about week 1. How do you get the 3rd lone pair? Acid-base mechanism. Okay? Everything is systematically done. Right now, I'm telling you, half of you cannot sit down and show the conjugate base of something. Please make sure you can. This is the conjugate base. That's the basic form. Okay? Which one of these forms will be favored? That is, what's the favored form of this at pH of 7? We got to know the pKa. pKa is 5. It's a carboxylic acid, about 4 to 5. I'm telling you 5. If we're at 7, which one's going to be favored, A or B? B will be favored because the pH is greater than the pKa. pH greater than pKa. You guys will get this backwards. You will say that this is lower than that, so it should be on the acidic side. No. No. Keep this in mind. This is a constant. Constants never change. Right? You know that, right? Constants don't change? It's a constant. pH can change. I can change the pH by adding in some hydroxide or adding in some other acid. I can change that easily. You want to look at the thing that changes. Where does it sit compared to the constant? And hopefully this makes sense. Do you agree that the variable is on the high side of the constant in terms of the numbers? It's on the high side of the constant. Well, the high side in terms of pH is what? Is that acidic or basic? Yeah, higher number is basic. It's on the high side of the constant, so the basic form is going to predominate. That's another way of looking at the summary. What if the pH was 2? That would be on the low side of the constant. And the low side is the acidic side. Which side would predominate? This, the acidic side, this species. Acetic acid in the blood exists like this. It exists as an ion. That's important to know because ions are going to be more soluble in aqueous. Blood is largely aqueous. It's a core component there is aqueous, not acetone, right? Water. Water with lots of other things in it. Some things down there, I think it's just a little review. We've said those things. Those things are also mentioned over on the free information page at the back. Lots of miscellaneous things. I hope that whenever you see this, that you say, well, the instructor must have thought it was important to include it in the handout to help illustrate something. I should look at it. Questions here are meant for you to stimulate and help you ask questions, and then you can answer them. You've got to learn how to ask questions and then answer your questions. Coding, the structure of coding. Starting to get familiar with organic structures, the architecture. Aromatic ring, is that ring aromatic? No, this ring's not aromatic. You've got other rings. There's also a kind of a ring 3 here, and there's also one that's sort of back here that's sort of there. Ether, hydroxy group, or alcohol. What is this? Tertiary amine? What's the most basic atom in that structure? The arrows are kind of giving it away. Right here. lone pairs here. Is this a good base? What we say were good bases? If not, let's say it again. What's a good base, typically? Anions. What's the only neutral functional group that's going to be a good base? Or neutral atom? sp3 nitrogen. Like the alkaloids. I showed you a whole page of those. Why? Because they all have sp3 nitrogens. sp2 nitrogen can be a little basic, but we know it's less basic because of the hybridization. There's your base here. Codeine is an alkaloid. It has alkaline properties because of that. If we react this with HCl, can we do a mechanism? Again, I like to circle my lone pairs. Most books and most instructors don't. I just think it reinforces. Okay. Once we move forward, I'll start saying over and over, when we begin our arrow, we start by saying these electrons. These electrons bond to the H. These electrons move on to there. What do you get? Well, the nitrogen is now bonded to the H. It's now a positive charge. You can do charges, right? And then what's the Cl become? Just a single atom now. The bond has been broken. It takes on the fourth lone pair. Here's your product. It's now a salt. And we call it the hydrochloride salt of codeine. Most drugs are given as salts. Why? It makes them more soluble in the stomach or in the blood. Assuming your stomach contents and blood is aqueous-based again. Okay? You all from Earth, humans? I predict you have aqueous. Okay? Which side's favored? Is this going to completely go here? What's the pKa of HCl? It's a very strong acid, like -5. What's the pKa of this? Or we can say, usually start with here, the pKa of sp3 nitrogen. Anybody got it yet? It's about 10. That means this is really what it's referring to. pKa, about 10. Which is favored? -5, which is this side, or 10? 10. How much is this favored by? 10 to the 15. What's that? That's got to be at least 100 gazillion. Yeah, it's highly favored because we're using a strong acid. That's why. Yeah, if you treat with HCl, you're going to have the hydrochloride salt. Now, how do you get this into like a powder form? Because if you're doing water, this is going to be soluble in water. Well, maybe you evaporate the water. There's a lot of other ways to do it practically, but we don't have time for all that. We'll do a little bit, but there's always other considerations. One on the back. Anybody heading to pharmacy school? Where are you all heading?
You said that we have any what in school?
Anybody heading to pharmacy school? Where are you all heading?
Vet school.
Nowhere?
Vet school.
Vet school? Every time I take my cat to the vet, they want to give me some drugs, and hopefully they know what they're distributing, and they know more than just reading the back of the label like I do. Right? You got the drugs in veterinary medicine? No? Pharmacology, I'm sure you'll take some pharmacology class or two. Okay, again, the back is free information sheet. Before we leave, though, you want to go back to the very beginning. Acid-base warm-up. If you haven't done this already, hopefully you have, but then everybody confident in this, showing this product now? Ask questions about acid base. Plenty of questions in the workbook. There's also questions in the on the DQ page. Any questions about those? Sucrose, et cetera? No? If there are no questions, let's move to our next handout. Alkanes Cycloalkanes. I ask you to print that on your own. We also have a purple handout. Okay, warm-up page there. Nomenclature. How we doing on nomenclature? Video? Any questions about nomenclature? Question?
For the propyls in the comment, it's like isopropyl, N-propyl. Do you take the I and the N for alphabetically or
No.
just the P?
No, we do not. Those would be like I dash propyl, N dash propyl. Typically when there's a dash, you don't consider the thing before the dash.
Okay.
Now if it said isopropyl as one word,
Yeah,
then you would take the I.
okay. So if it has a dash, just take the second part for alphabetically.
Correct, unless I'm not thinking of something.
Okay.
Like tert butyl, would be B, because it's a tert dash butyl.
The isobutyl.
Isobutyl, there's no dash, it's one word, so it would be I. Other questions about nomenclature? Okay. Next page, condensed formula structures. We have to get used to these condensed, or sometimes called linear formulas. They're basically typed out, so you can type it up on the computer, like word processing. Where you make your word processor can't do that unless you have a chemistry drawing program. But this is commonly done. We need to know how to decipher these and turn these into a structure. Okay. We often use parentheses, brackets to indicate multiples. Let's do this. Okay, the answer's already there. We've got two methyl groups. Two methyl groups bonded to what? If they were bonded to each other, that would just be ethane and that'd be it. You wouldn't have any other places to bond anything. Two methyls bonded to this carbon. There's that carbon with two methyls. Okay? By the way, very often as we move forward, I'll do methyls like this. Because it's just kind of quicker and it's just methyls of CH3, right? Okay? But then this carbon, we're building a good structure here from that. This carbon is bonded to what? Do you suggest? Well, there's an H here. The H can't be bonded between two carbons. It only makes one bond. The carbon is bonded to the H. And then what else is that carbon bonded to? The next carbon, that carbon is bonded to what? Two H's and an OH. And is all this good bonding? Yes. Carbon 4 bonds. Oxygen 2 bonds, 2 lone pairs. But then that we need to be able to show in a line bond, right? This is a carbon with 2 methyls, so that's a carbon with 2 methyls, right? And then it's bonded to another carbon, and it's bonded to an OH, right? And I just didn't draw in the hydrogens. Yes, there's 1 hydrogen on this carbon, right? Yeah, there it is. How many on this one? 2. And so we get that, and that's the same thing drawn over there. By the way, you guys tend to legitimate question I reckoned, but as we move forward, just because I drew this down doesn't mean I couldn't have drawn it up. I mean, over here it's drawn that way. That's just free rotation. We'll learn more about that going forward. You have to recognize that it's the same concept. So, any questions about how we went from there to there to here?
Do you mind, or do you care about the bond between the O and H, if it's shown or not, or it doesn't matter?
Here?
Yeah.
Well, only if you were asked to, like, okay, let's officially draw a Lewis structure. That's the only time I would want, might draw it out, put the lone pair on. I mean, see, I didn't even put lone pairs over there. As we move forward, we'll kind of relax a little bit. The outset, keep it very strict and formal and make sure, but then as we move forward, I assume you can. And if you can't, well then, you're getting left behind a little bit. But it's very common just to show it like that. You as students want to know, well, am I going to do it wrong and get deducted on quizzes and tests? No, because if it, but a formal show the Lewis structure, you need to show lone pairs and typically all bonds. Okay, for practice, do the next 2 on your own. We'll see how you did. All right. We'll look at the rest in due time. I want to move forward though because one of the bigger components of this handout, which by the way is our last handout before the first test, is conformations. So I want to get us going on that, then we'll come back and hit the other stuff afterwards. Conformations. Alkanes. Here's an alkane, 2 carbons, and the ends here are hydrogens. Okay? So we're looking at here CH3, CH3. By the way, that's condensed. It's also, you got to understand that these hydrogens are really on the outside, right? I could have shown this like this. But I guarantee you, any book is going to probably show it like that. You have to understand structure, right? These H's are all on the periphery, right? That's what I got here. 2 carbons, the H is on the periphery. But these carbons can rotate compared to each other. Typically, I just rotate here. I could also turn it like that, rotate the actual bonds. All right? But you get the same thing by doing this. All right? The bond can rotate. What we're going to be looking at is a relationship between like 2 hydrogens or 2 groups here. All right? And terminology. Let's go ahead and just talk terminology. We'll start fresh next time. Some introductory stuff here. This can rotate. Is there any difference between sitting like that compared to what's over here versus like there? Yeah, here these are lined up with each other. Yeah? You see that lined up? But if I turn it like that, they're not. That's important to know. Also terminology. What do you want to call it when they're lined up? That is, I really can't see the one behind it. So like the sun behind the moon. Eclipsed. That's an eclipse conformation. It's right behind this one. I can't see it. But if I turn it like that, now I can see both H's behind it. What do you want to call that? And don't say non-eclipsed. It's staggered. That makes sense, right? It's called a staggered conformation. All right? That's the type of thing we'll look at. We also need to be able to draw this on the board with this view. Because here we can't see that. There's no three-dimension, etc. All right? How can we draw this on the board? Another way. How can we draw this more of a 3D way? We do it what's called a Newman projection. Newman was a chemist at Ohio State who developed this way of drawing it on the board or on your paper. Okay? Sometimes I call it circle, circle, dot, dot. You guys don't know what that is. Okay, let's draw this. What do we see? Let's draw this right here on the board with that view. How are we going to do it? Right here. We draw a circle with a dot in the middle. Okay? The dot in the middle is typically, we're dealing with two carbons, two atoms, usually carbons. Okay? And you're going to be looking down the carbon. See, when I do this, I'm actually looking one and then two, down the carbon-carbon bond. First carbon comes from the dot. If these are all H's, what's on the first carbon? An H. It's going straight up. Now, it's actually not going straight up. It's actually going a little bit towards you guys, if you understand the tetrahedral, and you can look at a model. On the board, though, we're going to have to draw it straight up because it's two-dimensional. You've got a hydrogen going straight up. You've got a hydrogen going that way. And you've got a hydrogen coming this way. That's the front carbon. Yes, all three are coming a little bit towards you, but that has to be assumed in it when you look at that. What do you see on the back carbon? Look past the front. What do you see on the back? You see this carbon back here? How do you see H's? One H that way? One H straight down? Okay. The back carbon, we can't really see it back there. It's hidden by the front one. But you can kind of see, if this was like a disc, okay, you can't see back it, but you can see over the disc. Okay. You can see behind what comes out beyond the disc. And in the back we have, that's the front. Back you have an H here. Right? Remember, you can't see this disc here, it's blocking it, but you see the H coming off a little bit in the back. Same thing over here. You see H a little bit coming off, and then you see your hydrogen back there coming straight down. And that's a Newman projection of ethane. Now, we can also rotate this. Now, I can rotate the front or I can rotate the back. If I rotate the front, now we have that. And we'd have to draw another Newman conformation. Okay? We'll talk about angles here. What is this dihedral angle between these two hydrogens? Etc. Let's see, what else I can say before we dismiss. The purple is the outline that I'll be following. That's what we'll be going through. Halfway down, I asked you to draw some Newman projections, but we need to determine what's the best one. For example, what's better, staggered or eclipsed? It's going to be eclipsed. And then we have our handout stuff, which is our reference. Last questions, guys. Yes. You need to start learning some. For example, we mentioned water, carboxylic acid, pKa carboxylic acid, 4 to 5. Okay. Didn't quite hear you. Ask me again. Yeah, and that varies. I mean, they're super strong. typically the equilibrium is going to be pushed the other way when you're using a strong acid. Think about it. Because they're the most negative. Every other pH. Have a good day, guys.